This is a microchip. When you zoom in far enough, you find something that looks like a nanoscopic city. There are skyscrapers, hundreds of layers tall, and hundreds of kilometers of microscopic wires connecting everything. At the very bottom sit the transistors, billions of them. They are the ones and zeros that make every computer work. The chip functions by sending electrons from transistor to transistor. The smaller you make those transistors, the shorter the distance the signals have to travel, and the faster the chip can compute. You can also fit more of them into the same space, which means a more powerful chip. For more than 50 years, transistors kept getting smaller, and the number that could fit on a chip roughly doubled every 2 years. That pattern became known as Moore's Law, named after Intel co-founder Gordon Moore, who noticed it in 1965. It was one of the main engines of the entire technology industry. Around 2015, progress slowed dramatically. We might never have pushed past that wall if it had not been for a single company that builds the machines that save the path forward. This is a video about the most complicated commercial product humanity has ever built. It costs roughly $400 million. It is so strange that the best way to introduce it is with a thought experiment. Imagine you are shrunk down to the size of an ant and given a laser strong enough to melt metal like butter. In front of you, a tiny droplet of molten tin, roughly the size of a white blood cell, is shot past at about 250 kilometers per. Your job is to hit that droplet not once, not twice, but 3 times in a row within 20 microseconds. That is exactly what this machine does. It hits one tin droplet 3 times in rapid succession, heating it to more than 220,000 Kelvin, roughly 40 times hotter than the surface of the sun. And it does not do this once. It does it 50,000 times every single second. The people who run the machine say they do not miss 150,000 laser shots per second and essentially perfect accuracy. The same machine contains mirrors that are among the smoothest objects ever made. If you scaled one of those mirrors up to the size of the Earth, the tallest bump would be no thicker than a playing card. On top of that, the machine can overlay one layer of a chip on top of another and stay aligned to within about 5 atoms. Parts of the system accelerate at more than 20 times the force of gravity. For 30 years, almost everyone thought building such a machine was impossible. Yet it exists. Only one company in the world can make it. That company is ASM, and the machine is the extreme ultraviolet lithography system that prints the most advanced chips on Earth. To understand why this machine matters, you first need to understand how a microchip is made. You start with silicon dioxide, often from ordinary sand, and purify it into nearly pure silicon. That silicon is melted in a special furnace. A small seed crystal is lowered into the melt. Silicon atoms attach to the seed and grow into a large single crystal ingot. The ingot is then sliced into thin wafers with diamond wire saws. Each wafer is carefully polished until its surface is almost perfectly flat. The wafer is coated with a light-sensitive material called In a positive photoresist, the areas exposed to light become weaker and more soluble. If you shine light through a patterned mask, you selectively weaken parts of the coating. A basic solution rinses away the exposed photoresist and leaves the design imprinted on the wafer. From there, you etch into the uncovered silicon with chemicals or plasma. Then you deposit a metal such as copper to fill the etched lines and form the wires. The remaining photoresist is washed away and you have completed one layer of the chip. The cycle of coat, expose, etch, and deposit repeats for every layer. A modern chip can have anywhere from 10 to more than 100 layers. The bottom layers form the transistors and require the highest precision. The upper layers are mainly the metal interconnects that carry signals and power. By the end, a single wafer can hold hundreds of chips that are cut apart, packaged, and placed into phones, computers, and servers. The hardest and most important step is the moment the light shines through the mask onto the wafer. That step is photolithography, and it sets the limit on how small the features can be. At first, the idea seems simple. Light passes through the openings in the mask and is blocked everywhere else. But as the features get smaller, the gaps in the mask start to approach the wavelength of the light itself. Diffraction becomes a serious problem. Light waves spread out after they pass through each gap and interfere with one another. When the peaks of one wave line up with the troughs of another, they cancel out and create dark spots. When peaks line up with peaks, they add together and create bright spots. Designers actually use that interference rather than fight it. They work backwards from the pattern they want on the wafer and design the mask so that diffraction creates the desired image. The smallest feature size that can be printed is described by the Rayleigh equation. It depends on the wavelength of the light and the numerical aperture of the optics. There is a practical limit to how large the numerical aperture can be. Once that limit is reached, the only remaining way to print smaller features is to use shorter wavelengths of light. For years, the industry used 193 nanometer deep ultraviolet light. That wavelength worked well until around 2015, when further progress became extremely difficult. Moore's law was running into a wall. A radical change was required. And the idea for that change had been circulating since the 1980s. A Japanese scientist named Haru Kinoshita proposed using much shorter wavelengths, around 10 nanometers, in the extreme ultraviolet range. In theory, those wavelengths would allow far smaller features. The problem was that light at those wavelengths is absorbed by almost everything, including air and ordinary light. The entire system would have to operate in vacuum and could not use conventional refractive lenses. Kinoshita found a possible solution in special multi-layer mirrors that could reflect extreme ultraviolet light. Curved mirrors can focus light just as lenses do. After years of work, he produced the first crude images, but the scientific community was deeply skeptical. Many people simply did not believe the approach could ever work at production scale. Kinoshita later said the audience treated the whole idea as a big fish story. Similar research was happening at Lawrence Livermore National Laboratory in the United States, where scientists were studying multi-layer mirrors for other purposes connected to nuclear research. When those researchers tried to apply the mirrors to lithography, they also met strong resistance. Funding was uncertain, and the engineering challenges looked enormous. One scientist who presented the idea was literally laughed off the stage. Eventually, a consortium of chip companies and national laboratories kept the work alive with private investment after government support was reduced. By the year 2000, they had built a working prototype called the Engineering Test Stand. It produced a few watts of 13.5 nanometer light and proved that extreme ultraviolet lithography was possible in principle. But the prototype could only print about 10 wafers per hour. For the technology to be economically useful, it would need to print hundreds of wafers per hour, day after day, year after year. Most American companies eventually walked away. That left one company willing to continue, ASML, in the Netherlands. ASML had spun out of Philips in the 1980s with modest resources, little more than a shed and an early wafer stepper. It joined the early extreme ultraviolet efforts and eventually took on the task of turning the laboratory concept into a commercial machine. The German optics company, Zeiss, became the partner responsible for the mirrors. The first major decision was the exact wavelength. Researchers explored a range of possibilities and settled on 13.5 nanometers because that wavelength worked best with mirrors made of alternating layers of silicon and molybdenum. Those mirrors could reach roughly 70% reflectivity. After the light bounces off several mirrors and the reflective mask, only a small fraction of the original photons reach the wafer. That means the light source itself has to be extremely powerful. Creating that light is the heart of the machine's difficulty. Early approaches used synchrotrons or discharge plasmas, but neither scaled well enough. The method that finally worked is laser-produced plasma. A high-power carbon dioxide laser hits a target and creates a plasma hot enough that electrons are stripped from the atoms. When the electrons recombine, they emit light at the desired wavelength. The best target material turned out to be tin. Molten tin is forced through a microscopic nozzle under high pressure and broken into a stream of tiny droplets. Those droplets must be identical in size, shape, and spacing, and must travel at high speed. The machine generates 50,000 of them every second. A first laser pulse flattens each droplet into a pancake. A second pulse further expands and rarefies it. A third, much more powerful pulse turns the low-density cloud into plasma. The result is a flash of 13.5 nanometer light. The process repeats continuously. The laser itself starts as a weak beam and is amplified through multiple stages until it reaches tens of kilowatts, powerful enough to cut steel. The explosions create debris that would quickly ruin the expensive mirrors. The chamber is filled with low-pressure hydrogen that slows the tin particles and chemically cleans the surfaces by forming a gas that can be pumped away. The hydrogen flow itself must be carefully controlled. Too little, and the mirrors become dirty. Too much and the light is absorbed or the system overheats. The energy released by each plasma event creates tiny shock waves in the hydrogen, similar in some ways to miniature versions of the blast waves seen in certain astronomical explosions. Engineers used high-speed cameras and physical models to understand those waves and set the right flow rates. The mirrors are so precise that even tiny temperature changes would throw the optics out of alignment. Zeiss built an elaborate system of sensors and actuators that constantly measure and correct the position of each mirror to nanometer and even picoradian accuracy. One engineer described the pointing precision by saying that if you placed a laser on the side of a mirror and aimed it at the moon, you could choose which side of a small coin to hit. All of these pieces had to work together. For years, the power of the light source lagged behind the target. Customers grew impatient. ASML's engineers kept pushing. They refined the droplet generation, improved the laser timing with laser curtains that detect each droplet and fire at exactly the right moment, optimized the hydrogen flow, and added controlled amounts of oxygen to keep the collector mirror clean for longer periods. By the mid-2010s, the source finally reached the power levels needed for commercial production. The first extreme ultraviolet machines entered chip factories. Today, every leading-edge processor depends on them. The current low numerical aperture machines print features around 30 nanometers and process roughly 200 wafers per hour. The newer high numerical aperture systems use larger optics with a numerical aperture of 0.55. They can print even finer features and are already being used in high-volume manufacturing for some advanced logic chips. Light source power has climbed from a few tens of watts in the early days to several hundred watts today, with roadmaps pointing toward 1,000 watts and beyond. Higher power means higher throughput and lower cost per wafer. ASML remains the only company that can build these tools. A single high-end machine costs hundreds of millions of dollars and is shipped in dozens of containers on multiple aircraft. Thousands of suppliers provide more than 100,000 parts. The clean rooms where the machines are assembled allow almost no particles larger than a fraction of a micron. The story of extreme ultraviolet lithography is a reminder that some of the most important technologies begin as ideas that almost everyone considers impossible. Kinoshita and the early researchers were told their approach would never work. The American laboratories faced skepticism and funding cuts. ASML bet the company on a technology that took more than 30 years and countless engineering breakthroughs to bring to production. The result is a machine that fires lasers at tin droplets 50,000 times a second, reflects light from mirrors smoother than almost anything else on Earth, and aligns layers of a chip to the accuracy of a few atoms, all while parts of the system accelerate faster than a fighter jet. Without it, the progress of computing would have slowed dramatically. With it, the industry continues to pack more transistors onto silicon and build the chips that power modern life. The reasonable view 40 years ago was that none of this could ever work. The unreasonable people kept going anyway. Progress often depends on those who refuse to accept the limits that everyone else treats as permanent. If you found this look at one of the most complex machines ever built useful, hit the like button and subscribe so you catch the next deep dive. Turn on notifications if you want to be first to see new videos. Related videos are on the screen if you want to keep watching. Here is a question for the comments. Does knowing how difficult it is to make the chips inside your phone change the way you think about the technology you use every day? Let me know what you think.